And what I'd like to do is I'd like to get the presentation to start. I'd like to tell you about what we're doing at BARC. These are the folks who were at BARC. We had 2 interns last summer. Some of the work I'll be talking about is done by the 2 interns, and Eric Riddell. We have 2 new interns this summer. We're in that big black building right across from the bus station in downtown San Francisco. Gordon Bell and Jim Gemmell are trying to make a contribution to the area of telepresence. And their premise is that telepresence is what computers are good for. And the telepresence can help you do both space shifting and time shifting. This is not a novel concept. Everybody has a VCR, that's time shifting. The thing that the VCRs we have, though, aren't really very good VCRs. What you'd like is a VCR that, or a recorder that records things and basically digests it for you so that you can see the 1-minute version of the basketball game or the 10-hour version of the basketball game, and anything in between. The most popular website that we've constructed, and I think it's one of the most popular ones that research has, is the ACM 97 capture that we did last year. And there were 17 keynotes at that 50th anniversary. One of them was Nathan Verbal, another was Gordon. But there was William Perry talking about how computing had made the Nuclear Test Ban Treaty possible, and Rod Sterling and Murray Gell-Mann, and a lot of interesting.
And don't forget Raj.
Yeah, Raj Reddy. Excuse me. Oh. The illustrious Gordon Bell, who incidentally is in Paris right now and having a good time, probably falling asleep. That website has turned out to be very, very popular. More people have visited the website than went to the conference. And more people have spent more time at the website than spent time at the conference, which is probably even more compelling. And Gordon had a bet that this would happen by, was it 2 years? Yeah. And it didn't take 2 years. It took about 6 months to win the bet. So,
who did he bet against, Raj?
I'm not sure. Who did you bet against? Do you know?
He usually bets against Raj.
You need to get back 1 free dinner.
Sometimes he just bets.
So the
tools.
Let's see. So the first thing we're going to do is Jim Gemmell originally was not going to be here, and Jim was going to give his presentation from San Francisco, and he was going to telepresently present this without flying. Well, the simple fact is that Jim needs to be here for other reasons, and so we thought of Jim going down the hall and presenting down the hall here, but we decided against that. So Jim's going to stand on the other side of the room.
I'm telepresent for women.
Yeah, but what I want to know is, why is Gordon in Paris?
And so what Jim's going to do is show us, talk about multicast, but also while he's talking about multicast, we'll be using his multicast software to do a PowerPoint presentation. So, Jim, shall I get started?
Yeah, so get started. So just take note when Jim clicks on OK here.
Okay, so this is a tool that's popped up that's in the under the Tools menu, and it's multicast PowerPoint. And I say OK, that I do want to subscribe to this.
Receiving slide master, I just want to remember that because I'm going to refer to that later. And you can just say OK again, Jim. And OK. And it'll fire up. Okay, so I want to talk about the work that I've been doing for scalable, reliable multicast and telepresentations. I've talked about quite a bit of this already, so a lot of the MSR people will be familiar with it. But I'm going to explain what reliable multicast is and why it's hard to scale. And then talk about 2 protocols that we've been working on, the FCAST file transfer protocol and the ECSRM reliable multicast protocol. And then talk about how we can apply this to layered telepresentations, of which this is a demo right now. Jim's actually tuned in via multicast over there, so we could have umpteen viewers actually tuning in as well.
Would you normally give him audio too?
Yeah, we were going to set this up with an audio and a video feed, but I am the audio and the video feed.
Much better fidelity than you get ordinarily.
Yeah, how about that? So just for those who aren't familiar with multicast, this is the story with unicast. If I have to send something out to a bunch of interested receivers, and at the bottom there's a couple who aren't interested. I have to send it over and over and over and over and over again. And the links see the traffic repeated on them. Now, on the other hand, the way multicast works is you send one copy, and it's up to the routers to replicate that. And it goes out to everyone with the minimal traffic. Pardon me, I'm still getting the hang of the touchpad down right now. So, IP multicast operates like a prune broadcast, and oh dear, this is going to be harder than I thought. And it's unreliable. So if we want to deal with adding reliability to it, we have to build something on top. And the reason this is an issue for telepresentations is, for instance, with the next show, when they do audio and video, they say, well, if you drop a video frame, tough luck, you don't notice. And even if you did notice, by the time we went to the work of going and fetching the frame and bringing it back again, you'd be on to, the next 20 frames. But when I bring up slides, I talk about it for a long time. So we need to do something about reliably transmitting them to you. So why reliable multicast is difficult to scale is because, for two reasons. First of all, if the sender is trying to keep track of all its receivers, such as it would do if you open a whole bunch of TCP connections, you have a state explosion. So as I grow the number of receivers, I have to grow the amount of state at my sender. Secondly, as the receivers communicate with the sender, you can have a message implosion back up to them.
It's my screensaver. Excuse me.
Uh-oh.
Keep-
So one method employed by a lot of schemes is to make it receiver reliable. That is, it's up to the receivers now to keep track of when they've missed a packet and to ask for it, so the sender just forgets about keeping state for them. So good, we've avoided state explosion, but we still have the message implosion. There's a bunch of approaches to making things more scalable. You can build up a hierarchy, and so now a parent is only concerned with his children and vice versa, and by bounding to the degree of the tree we can scale. We can implement forward error correction and try and solve some of the losses that way. We can use a method called suppression, where in a receiver reliable mode, instead of asking right away for something when you've missed it, you multicast it and you wait a random amount of time hoping somebody else will, which I'll talk about a bit more later. Or you can do a hybrid of these approaches. So the two protocols that we've got, FCAST uses FEC only, and ECSRM is a combination of suppression with FEC. Yeah.
I'm a little lost in who we is. Is we BARC?
Yes.
Or is we the community?
We is
You and
BARC.
your competitors.
We is BARC.
Okay. Are there other people trying to do much the same thing? I assume so.
Oh yeah, yeah. There's a lot of this in the last year. This field's kind of going crazy, so there's lots of people working on it, and there's examples of hierarchical schemes from all kinds of people and very similar work going on all over the place. So I'm going to show the type of FEC that we're using. It's actually erasure correction, not error correction, because the multicast packets are discarded if there's anything garbled in them. So we only have to deal with correcting losses. We start with K original packets. We do an encoding so that there's N of them, where N is typically much bigger than K. And then if we can receive any K of those N packets, we can reconstruct the original K. And so we have a code that's based on Reed-Solomon codes right now, but there's lots of different schemes you could use, but as long as they fit this general flavor here, it'll have the properties we want. So the FCAST protocols for pushing files out, our motivation here was seeing how the Internet Explorer releases were bringing the Internet to its knees and cutting off UW from the Internet and all kinds of nasty things. And we said, hey, what if we could multicast these files? But now we need to be super scalable. We need to, people have typically scaled up to about 1,000 so far. We want to scale up to millions. How can we do that? So we looked at how could we just push the files out with FEC only. And the idea here is to transmit the files in parallel as follows. So if I have a bunch of files, 1, 2, etc., I take the blocks of those files and I slice them up into groups of K each. Then extend it with the encoding. Now it's time to start transmitting, so I transmit the first from the group, and then the next, and so on until I transmit OK. And then I keep going, transmitting encoded blocks to the end, and then I loop through and keep sending continuously. Now what a receiver needs is any K from a given row here. And as soon as it has K, it's done. So a sender will be sitting here having the files in the FEC and looping, doing that over again. A receiver can join, pick up the packets that it needs, and drop out. So here's a low-loss receiver. It doesn't take too long. A high-loss receiver can join in and listen longer and get more FEC packets and drop out.
Can you tell them the NT story?
Yeah, so we have NT people assigned to this, and the idea, besides that they want to ship it with NT, is also that they want to use it for the NT builds. Right now there's something like, I think, 14 servers with big RAID arrays on them, and they're using this for the NT build, so when they build NT every night and all the developers need to get a new build of it, they're all hitting these servers and dragging it down. And what we want to do is use FCAS for that, so where it's, I think it's about 170 megabytes everyone needs to download every night. Instead of needing 14 servers, you know, high-powered, we could do it from probably this machine. Get rid of all of them.
How big are your blocks? You said you divided into blocks, so 1K blocks.
Yeah.
Is that sort of optimal? Or?
Well, it's reasonable for Ethernet, and it works nice when we get to dump it on the disk and we want to do raw file transfer.
And the other premise is that you can take Internet Explorer and run a broadcast at 28.8, a broadcast at ISDN, it's broadcast at T1 speed, and rather than having 1 million downloads of 20 megabytes in the space of a day or two, we would fundamentally, every 20 or 30 minutes, we'd start another 28.8 broadcast, and so on. So the bandwidth would be in the megabytes per second as opposed to the hundreds of megabytes per second. I mean, when we put up Internet Explorer, it completely saturates the bandwidth of www.microsoft.com.
So you essentially have channels you tune into for doing your downloads.
Yeah.
Depending on what your bandwidth is, because well,
Yeah, so you target them for certain receiver speeds. And we're also looking into, in the future, getting into layered schemes where you split up the data and there's several simultaneous multicasts going on. And if you want more, you'd actually tune into 2 channels at the same time. We haven't got that yet, and there's not a lot of incentive to do it for something like Internet Explorer. I mean, it's a big enough deal that, hey, if we used 4 multicast channels, we probably wouldn't feel that bad about it compared to what we do now. So that was FCAST. The second protocol that we worked on is ECSRM, Erasure Correcting Scalable Reliable Multicast. And so this is combining suppression with erasure correction. So to go into the suppression in a little more detail, you delay a negative acknowledgement in the hopes that someone else does it for you. So rather than when something gets lost and 1,000 of us saying, oh gee, I lost that, and pounding the sender, we all delay and one of us will multicast and the rest of us say, oh great, that guy did the work for me. The NACs are multicast. After you NAC, you reset a timer and wait to see if you get the repair. If you heard someone else NAC, then you pretend that you NAC'd yourself. They did it for you. The variant that we've added to that is to put FEC into the mix. So now instead of NACing on individual packets, we slice things up into groups just like in FCAST. And what you do is you NAC how many packets you're missing from a certain group rather than individual packets. So you say, oh, you know, group A, I'm missing a certain number. And now a NAC of a certain number suppresses all the other NACs that are the same or less. So for example, if I was missing 2 and I heard you NAC for 3, great, you know, you've done the job for me. But if you NAC for 1, then I still need to do something. Then the sender, instead of resending particular original packets, sends out the number of FEC packets that's needed. So here's an example. Here's a sender blasting out 7 packets. Somewhere down the wire, packets get lost. And here's 7 different receivers who each lost a different packet. They all set their timers and say, oh, I need to knack for that. And eventually someone's timer goes off, and so they say, oh, I'm missing one from group number 1. This is multicast to everyone, and the rest of them are suppressed. So they don't bother knacking. Now this is hand waving because some of the knacks could be lost, and so there's kind of a modulo reality thing here, but to gross approximation, this is what would go on. Then the sender generates an erasure correcting packet, sends it back up to everyone, and they're all able to use that to decode the entire group and get the original packets that they're missing. So compared to just suppression alone, where you would have needed 7 knacks in that situation and 7 separate repairs, this took 1 knack and 1 repair. The particular motivation for this was Jim Gray coming and sitting in my office and saying to me, gee, when you get into these really big groups, no matter what you send, somebody's going to lose it. I went, yeah, that's a real problem. And so at one point I took some really small number and said, well, what if there was a 0.0001% chance of loss and you had a group the size of 1 million? It boils down to, yeah, someone's still going to lose it somewhere. And what that would mean is that with just suppression, you would end up having to resend everything. So you've scaled in the sense that maybe the entire thing didn't blow up, but your performance got cut in half, which is probably not what your customers thought you meant when you said you could scale. So without FEC, that's what could happen. We could lose half the traffic to repairs. But with this, we bounded, in the same situation, we bounded it down to 1/8 by using the FEC instead. And we've also reduced the NAC traffic by a factor of 7. So it allows us to scale a lot further than with just SRM. So here's a plot that I did. This is a simulation from a student at MIT showing the minimum and maximum traffic seen by any node in a 112 receiver network, which is, we're still having troubles getting simulators that can handle large enough numbers for us. So SRM, kind of the best case is here, and the worst case is a lot of traffic up here. ECSRM, the worst case is underneath the best case, and the best case for ECSRM is way lower. Also, SRM has a long tail to finish sending off all the various repairs that people need, whereas due to the FEC being able to satisfy a lot of different losses, it drops off a lot quicker. And here's the NAC traffic is similar. There's some spikes in ECSRM that get up in the SRM category, but for the most part, it's considerably lower. So how do we use this besides just the FCAS file transfer application? In telepresentations, the way we use it is in a layered transmission that is on 2 different multicast addresses. So on one multicast, we do a FCAS to the slide master. That's your slide that has maybe a background on it, what fonts, color schemes that you're using. And then using ECSRM for the live data, we send out the control information, like when I'm flipping the slides, the actual content of the slides as they're happening, and any annotations if I had scribbles. It's not working in this version of it, but we used to be able to scribble on top of it and have it show up too. So the idea here in splitting it apart is that when somebody joins late, we don't want them to impact the whole group. So if Jim had just come onto the session now and tuned in, he'd first go to the FCAS multicast channel and pick up that slide master. He does that independently of everybody who's currently watching the session. So rather than them seeing all his repairs chew up their bandwidth, he's doing that without any impact. Then once he's got the slide master, then he joins the live data and tunes in. So in the future, we'd like to see how we could also integrate hierarchy with ECSRM. We've been talking with Cisco about their PGM scheme and also thinking about some ideas of our own. Now we, meaning myself and the NT networking group. Also wondering, do we need 2 protocols? FCAS is extremely efficient because it doesn't require any back channel information, so it's super scalable. But on the other hand, it's very awkward to deal with dynamic data in it. ECSRM is not as scalable, but it deals nicely with dynamic data. We'd like to see if we could maybe throw away one of the protocols and just make it do with the other, but that's a hard problem right now for us. And now we're going to do a demo of just FCAST itself.
Okay. In show. So I come down here, is that right, Jim? And hiding down here behind the scenes is your FCAST receiver.
Right. And so my FCAST sender is already running, and it's just churning along, generating blocks. It has no idea when this receiver joins or drops out. It just continually multicasts.
So we've got, you know, is it packets received? Bytes
Packets received.
Packets received, packets decoded, packets dropped. What's that say?
Stray packets, that's from other sessions. And
Redundant packets?
so lost is what we're interested in. Dropped means it got to your machine, but the CPU couldn't keep up with things. And lost means we actually missed something.
So I'm going to start receiving,
Yeah.
and now I'm going to disconnect the Ethernet. And we're not receiving anything. And then I'll reconnect it. And now the lost number goes up to 544 packets missing. And I can disconnect again. And then the lost number went up to 713. And we haven't gotten any redundant packets yet, right?
No, it'll be near the end. We're doing about 3,000 blocks. This is the executables of Front Page and Front Page Explorer.
Jim, in the beginning, it was dropping a lot of packets. Now it's not dropping any.
Yeah, it's writing things out to disk as it receives them, and so at the beginning, while it was opening files and stuff like that, if packets were coming in, and it was having to drop them on the floor.
So something to appreciate is that NT has a test environment that's about 1,000 machines. And they come in every day at about 5 o'clock with 170 megabytes worth of NT that they want to send to all of those 1,000 machines. Do the math, that's 170 gigabytes. That's a lot of network bandwidth. The machines are spread all over the place. And they could multicast that thing in one channel continuously and send a lot fewer bytes than sending it. Right now what they're doing is unicasting it to each one of those machines. And it uses a set of machines that would fill this room and are quite expensive. And Internet Explorer is that scaled up by a factor. I mean, this would save Internet Explorer broadcasts about a factor of 1,000 during the first 2 days.
There was also a proposal, I don't know where I heard it, that you would multicast to all the web TVs of all kinds of content that
Yes.
people might want, and they can pick up whatever they want.
Exactly. And that needs to have a reliable multicast. So,
Right.
so the received was done. And can we summarize? There was, what is it, 40? I'm surprised there's only 47 redundant packets. What?
Yeah, well, it did pretty good.
Wow.
So redundant packets in this sense is, from each group you needed K packets. If you had to listen to K+1 or K+2 in certain groups, those packets were redundant. You didn't need them, but you were waiting to get a packet from the group that you did need data from. And so that's what redundant is.
Does this require anything unusual in the routers? Or is
IP multicast support in the routers.
standard?
It's like shipping in most of the major routers now. It's not enabled in a lot of networks, and it's kind of going up the ramp of deployment now. Our network is multicast enabled as of now. The corporations are turning on a lot faster than the internet. The UUNet people turned it on in one direction for NetShow, and they sort of have a back channel. So FCAST is attractive in that sense too. The VCSRM wouldn't work there.
Firewalls are problematic. Multicasting firewalls is. But unlike NetShow, you can sit with PowerPoint on your desktop, and you can, if you're on the right side of the firewall, you could give your desktop presentation to everybody on the internet whose firewall will let multicast this through. And all they have to do is download a viewer, actually a plugin for PowerPoint from Jim's homepage. So I don't know how many of you have done NetShows, but it's quite an experience to do a NetShow. You have to have a staff, and people have to come and videotape, and then people have to edit the results. And it's very server-centric. It's not desktop presentation. This is very easy to do.
So Jim, when is this going to transition from the research lab? You're making it sound so attractive.
It already has.
The NT.
Plug it in.
We've got an NT developer working on it right now. Are you talking about the FCAST or the presentation part of it?
Both, I guess.
The file casting part of it is basically there, and actually we've shipped it to the test lab right now. But they have, their priority for the bug list of NT5, so we're waiting for them to get through that before they check it off.
So will it get into 5?
It's not supposed to by the deadline rules, and it's not clear to me that NT5 needs to be the ship vehicle anyhow. We could just post it on the web, and it would just be a little applet that you download.
So we take the web down just one more time. Tell everybody down.
That's right. Well, this is tiny. This is tiny though. This little thing is, I don't know, 100
And
K.
the PowerPoint viewer can be downloaded right now. So you could take your PowerPoint presentation and multicast it to everybody at Brown right now this minute. I mean, well, in about 10 minutes.
Can the client be constructed as IE plugin?
The code that I wrote right now needs PowerPoint to work. This originally started out as a project with PowerPoint. It was going to be integrated with them. So.
Because it seems to me that the trick here would be when you go to download something, it automatically first downloads the.
I think.
Oh, I'm sorry. You mean the file now?
The file.
Oh, could it be in IE? Oh, yeah.
It'll just become the default mechanism.
Yeah.
So that when you click on download this thing, instead of download install, it just downloads that first, and then just starts listening to the podcast.
Yeah, and I mean, I think eventually we want to try and give incentives to people to use multicast and say, hey, this is available, a day earlier if you tune in via multicast, so that we push the load off our servers.
The incentive is make it the only way they can do it.
Well, people will make copies eventually, but that's great. They'll be mirror sites for us. Yeah.
What do you think the future of multicast is?
Wow, that's an open-ended kind of question.
Think it's going to survive?
Well, it'll definitely survive. In the short term, it's being adopted fairly quickly now by corporations, and there's a lot of, ideally, from a telepresence point of view, I'd love everything to be on demand, and I'd pick it up that way, except for certain things that I want live, like maybe news and stock feeds and things of that nature. But for the most part, I wish it could be on demand. But on the other hand, when you just look at sheer capacities, and what we'd have to provision in our networks to let us all watch, video on demand, it scares us off pretty quick, whereas if we multicast things even periodically.
I guess what I'm hearing is that there's sort of more and more interest in moving this multicast capability up into the app layer rather than leaving it all down in the hardware. Does that make sense?
I'm not sure.
Well, having sort of proxy servers and things like that sort of manage the multicast traffic more intelligently, handle the link redundancy issues, and so you instead of connecting to a server somewhere that is sort of multicasting traffic to all these different places, you connect to some proxy that finds the server you want, manages the balancing of traffic across a variety of links. So it's more of an app layer thing. So if there were 100 people watching something this end and the link had 10 megabits per second bandwidth, I would sort of manage that there was somebody else who wanted to watch, there's only one person watching some other, so there's a whole quality of service issue and all those sorts of things which are sort of better managed at an app layer is the argument.
Well, yeah, quality of service is a whole other issue. You also brought up just how you would discover the sessions and so on, and so we need whole kinds of APIs for doing that.
So the argument is that sort of, multicast was sort of seemed like a really good idea, but it sort of doesn't go far enough by a long shot, and therefore.
Well, but let's see how far it takes us without doing
absolutely.
all that.
All right.
I mean,
really interested in your opinion only.
If we can scale things by a factor of 1,000 right off the bat,
absolutely.
I'm not really going to complain.
And maybe obviously it's a combination of both, right? I mean,
but I think what you're alluding to is we want to get into maybe some kind of mode where we automatically detect, oh, we've crossed a threshold. There's more than 100 people after this. Let's automatically multicast things. I think some people at Georgia Tech have looked at stuff for that in terms of automatically multicasting popular web pages and stuff like that.
Well, another question would be, let's say I've got a server and it's serving out this multicast session, and so in your tree, something breaks. Does multicast support rerouting and
yes,
it does a leveling?
Yeah. So all the transfer mechanism, is done just IP basically.
Okay.
So it's done for you. The apps don't worry about any of that.
If you talk about some of these people or everybody downloads Internet Explorer, would it make sense to cache the information at some lower node so that you...
Caching absolutely makes sense in these situations.
So that you sort of...
The fact is, it just isn't happening enough.
Are you familiar with the adaptive web caching work at UCLA?
Not that.
Lisa Zhang's been doing.
Really? Is it
She used the IE situation as an example of that. They talk about ways to store stuff at the routers and have routers just move it forward a lot like.
Oh, I see. Yeah. Well, getting routers to do that is There's a lot of interesting schemes with dreaming about routers doing things for you. But
Maybe we should go on to the next one. So, again, Jim's PowerCast stuff is on his webpage and at BARC, and he's also got a version of the MBone that works on Windows platforms. That's there, and the FileCast stuff I think is not there yet, but that's because it. And we're trying to find a quote release vehicle for it. But NT5 has left the station, and it didn't make the NT5.
actually, I'm just trying to get permission from the NT people to do that. I want to post it on the web and call it a research release and let people play with it.
So this is a completely different project. We spend a lot of money on testing. One estimate is that Microsoft spends 60% of our R&D budget on testing. So what can we do to make testing more automatic? And Don Slutz, who did this project, is a database expert. And what Don's idea is let's run the SQL parser backwards. If you run the SQL parser backwards, you end up with a SQL generator. So you go and look at a database, and you say, okay, here's the possible table names. Here's the possible column names. And in fact, you can look in the database and see the possible values. And so he makes up SQL statements. And he makes up SQL statements that are this long. Okay. SQL statements that you and I would never dream of. We have no idea what they mean. And he gives them to our SQL system. And he gets back an answer. He doesn't know whether it's the right answer or the wrong answer. He has no idea what the statement means. So he goes and gives it to some other database system, like the one from IBM, or the newer SQL that we have, or Oracle's system, or Sybase's system, or Informix's system. And we have all of these systems running on a computer in San Francisco, all storing exactly the same database. And he sees whether they get the same answer. If they get the same answer, then it's probably the right answer. If one of them gets a different answer, and everybody else gets the same answer, it's probably 4 out of 5. They probably. So it's being used in SQL testing, and at the last count, the problem number is probably now 580. The testing people love this thing, but I guess I'll show you the next slide to explain why. But they basically find a lot of bugs. So here's a typical SQL statement. Okay. And you go to the testers and you say, or the developers, and you say, this statement gets the wrong answer. That's what they do. That's exactly the reaction. And after they stop laughing, they say, well, and when the answer happens to be that the system crashed, which is not an unusual thing when we first get started, but it's now much more unusual, they get a little more serious because now they can look at a dump or something. But when it comes back with actually the wrong answer, then that's, it's actually not very helpful. So the key thing is to find the simplest SQL statement that gets exactly the same error. So what he does is he got this parse tree and he starts pruning the parse tree. And it turns out that this was the simplest SQL statement he could find that got the same error. And in fact, this pruning works actually very well. Usually this thing finds problems, which have actually a pretty simple explanation for what the problem is. So Don has put lots of knobs on this thing. RAG stands for Random SQL Generator. And it's stochastic testing of SQL. We've found thousands of bugs in BARC. We found thousands of bugs in Oracle. We found thousands of bugs in DB2. We found thousands of bugs in Informix and Sybase. And we've thought of publishing a website of maybe 100,000 bugs in DB2. Things that we do right that no one else does right.
100,000 known bugs.
Known bugs. And we believe that this would bring the development organizations of all of our competitors to their knees. It would also discredit the entire database industry, I believe. And it's a little bit like nuclear war. It's not that hard to write this program.
That's right.
And I'm sure that they would publish 200,000 of our bugs. So we are not going to do that. But it's an interesting concept. The other thing that Don is doing, which is actually also very useful, is that he can generate lots of threads in parallel. And he can submit these things in little packages called transactions. And so each thread is doing a whole bunch of SQL statements. And if the system deadlocks, that's bad. Okay, so you could run this and come back. But at the end of each of these transactions, he aborts the transaction. So if you abort a transaction, it's supposed to be a no-op on the database. The database is supposed to go back to the way it used to be. So if he comes in the morning and the database is different than the way he left it the night before, either because it's deadlocked or because some tuples are missing or some tuples have been added, that's a bug. Okay. Those bugs are hard to track down, but at least you know you have a problem. And so that's another way of doing testing, and that's turned out to be very useful. And in fact, it's found bugs in space allocation and the recovery code, things like that. Don, you want to add anything? Don's sitting back there in the back of the room. If I got it more or less right?
Yeah, that's right.
You know, these managers, they all. So the key idea here is that if you run 4 tests, and 3 of the guys get answer number 1, and the 4th guy gets answer number 2, then the 4th guy is probably wrong. Now, an interesting case of this is that there was a query in which 3 of the guys got answer number 1, and the 4th guy got answer number 2. And the SQL standard was ambiguous. The 4th guy was IBM. We actually asked the guy who invented SQL. We asked Chris Date, who writes books about it. We asked lots of experts. We got not just 2 answers back, but 4 or 5 answers back about what the right answer should be from human being experts. It wasn't a very complicated thing. It had to do with corners of the language. And in fact, the SQL spec was rewritten to make this the right answer. The rough estimate we have is that there are, Microsoft has a regression test suite of about 7,000, more than 5,000, less than 10,000 SQL queries that they use to do their regression test. It costs about a half hour to make a test, and then once a test is made, it just then gets run again and again and again. Our other friends of ours in the database industry have test suites in that range of, say, 10,000 queries that they run on a regular basis. It looks like Don can generate test suites that have many, many more statements and much wider coverage. And this has been an experience that people have had in other areas, that the code coverage of test suites that aren't built with a coverage tool is lousy. And this is a way of generating test suites that have good code coverage. So, but just as an experiment, he generated 60,000 select statements. He found 17 of them were suspect, like this. He examined 10 of those suspects and found 4 bugs. And fundamentally, it looks like he can find a new bug every 30 minutes.
So, Jim, I'm sort of lost at this point
Sure.
as to what the implications are. On a surface level, you're scaring the shit out of me.
Especially since people run elections with this stuff.
I was going to say, there is a hell of a lot of mission-critical and life-critical stuff entrusted to databases.
Mm-hmm.
And you're telling me that they don't just dump core, but return erroneous results at an alarming frequency.
Mm-hmm.
That is really a national problem.
Yes.
So what are
And that's why we spend 60% of our money testing, and we still don't do very well. And people think that we do a lousy job. We don't even test the code at all.
Well, there is another viewpoint of this.
Wait, let me finish my question. So how many of the sort of bugs that occur on a routine basis in fact result in erroneous information versus the system doing something nasty that is catchable?
Don, how many of them are wrong answers as opposed to system crashes? I mean, most of the bugs we find, in fact, are wrong answers, I believe.
What about
What's the wrong answer? Crashes have gone away. There's more and more releases. People who write sensitive applications usually test a little teeny bit of SQL they use very well.
So these are all tricky cases at the corners, as Jim said? Or do you even get some mainstream kinds of queries?
In one vendor, there's a power function, and 5 squared was 24.
Whoa.
It's round.
It's only the bank that
I can't begin to.
And that vendor is, in fact, the one you would least suspect of that.
Microsoft.
No, you might think Microsoft. That's not us. It's IBM. Is that right, Tom? That was DB2?
Pardon?
Was that DB2?
DB2.
Yeah. So, I mean, listen,
That's
there's...
not an exotic bug, exactly.
No, it's not an exotic bug, and they do the best they can testing. And I mean, this is a travesty. You're right, and there's very little research in this area. Frankly, there's some, but relatively little. And it's when we started, we were completely ignorant about the literature, and we're now less ignorant about it. But what's that?
Given the potential that you alluded to for mutual assured destruction, are we going to share this with them and sign some agreements that we won't publish each other's bugs?
No. In fact, Don has written a paper, and it's going to appear at BLDB, Very Large Database Conference, and we're talking about this in public. And it's easy to clone this program, and I'm encouraging people at universities to do it. And I think our products have gotten enormously better because of this. And I think everybody's products will get better for it. And it's our responsibility to just we have to do more research and testing, and we have to do better research and testing. And it would be better to have correct programs to start with.
Yeah.
Yes, I'm sorry. You made a statement a few minutes ago about code coverage that I didn't quite follow. You said that I certainly agree with the first half of your statement, which is that our code coverage today is lousy, and none of the test suites that we use do a particularly good job of encouraging code coverage in our testing.
Well, let me amplify what I meant by that. I used to work at Tandem. Tandem was very concerned about quality, and Tandem made the following deal with everybody else. He said, if you'll give me your test suite for C, I will take all of the test suites and unify them, and I'll come back and tell you how much code coverage you have and how much code the union has, and I'll give you the union. And so he got almost everybody's test suite for C. And the code coverage was 15% of the parse tree. I mean, there were huge areas, like exponentiation, as a matter of fact, is one of the things which simply wasn't in it. And so when humans construct test suites, and when they construct test suites based on bugs that have been found or reported, they end up not having very good code coverage. And so this guy then methodically went and built a test suite that in fact gave good code coverage of A, the compiler he had, and B, the syntax tree. Because code coverage doesn't necessarily take you around the loop twice, which turns out to be very important that you go around the loop more than once.
Okay, so two-part question. First part is, how are you actually quantifying in your deployment of this that it's giving you better code coverage?
This is actually
And
language coverage, right?
Yes.
And the second part is, are there specific tactics and methods that you're using in developing new tests using this system to get better code coverage?
This is actually language coverage. In other words, what percentage of the language are you
Right.
Well,
covering?
there's language coverage and code coverage. We haven't
Well,
done
okay,
any
so I
of
mean, in either case, how are you quantifying what this coverage is if you're getting?
Haven't quantified it yet.
Okay.
It's so easy when you go up to Alaska on a gold rush and you find nuggets everywhere.
Yeah, I
Okay,
understand.
you just rush to the assay office and file a claim, and then you go back and start taking your wheelbarrow. And we're in the wheelbarrow state right now, but we will get to the point where we need to. I mean, right now, my sense is we have very poor coverage. I could quantify it.
And you know what, I don't disagree with that. In fact, I totally agree with that.
But there's huge parts of them. In fact, I guess the next slide says there's big parts. Patents and papers. I mean, patent will do the idea, but I mean, I don't think we're going to prevent anybody else from doing this. And lots of other people in Microsoft are interested in this. There's been sporadic stochastic testing in other parts of Microsoft, and
That's
a
quite
million monkey kind of testing.
Right, there's quite a significant effort in monkeys.
The hard part is, though, I mean, with SQL, you have something where you can get this parse back out.
Right.
Yes, you've got a reference model.
Yeah, exactly.
Which is actually kind of fuzzy, but
If it crashes, you don't need that.
Pardon?
yes, if it crashes, you don't need the
That's
reference
true.
model. Crashing is bad.
Although oftentimes when you crash, I mean, it may be hard to trace it back to what actually caused it, right?
Right.
No, it isn't.
But there is a library
You have
that
to
will
import.
crash most Unix systems, and it's published by some guys at the University of Wisconsin. And it's been, and who was it? Bart Miller. And he built this library 10 years ago, and he recently wrote a paper 10 years later. And Linux is one of the few systems that survives the test. None of the commercial Unix systems survive the test. And the test has been published, been in existence for 10 years, and none of the vendors has taken the time to fix it.
Jim, can I suggest when you write your paper and give your talks that you get PR involved, because this is a great positive statement about the company.
Yes.
We're willing to share this.
So Jim, the related anecdote. You may remember William Keeman, who used to be
Sure.
still at DEC.
Yeah.
He did the same thing for compilers about 4 years ago when I was visiting him. He essentially generated all kinds of tests, like strings that are 72 characters long, which would kill the compiler.
Right.
And he generated a whole list of these things. He would give it to the manager in charge of the compilers. They thought he was a troublemaker. He said he immediately got fired because the issue to them was the obscure situations he was coming up with. They said are things that would never occur in real life, and they've got time pressures and all kinds of other things. They didn't want to be bothered by these bugs. So the issue is going to be ultimately some kind of a stochastic way of determining which ones of these long lists you might generate, like you did, are likely things that an average command anybody would have used, and the other ones which are so obscure that even if it is there, it's 1 in a billion that it would trigger or something.
So I'm very near the end of the of my hour.
Can I ask one more
Yeah, sure,
question?
absolutely.
Do any of these tests fail non-deterministically? That is, you run them twice and sometimes it works and sometimes it doesn't? Or is it always completely
Well, there's one
deterministic?
interesting thing, which is that different vendors will fail differently because it's a non-procedural language. So one guy may get a divide by 0 and the other one doesn't. And that's an interesting phenomenon. But the concurrent tests definitely are stochastic. That is to say, if you run the same test again, timing may work out differently. But I think it's it's not common for you send the query to SQL and then you send the same query to SQL and you get a different answer.
I've done some rerunning, but not much. I mean, I try it on different versions. There's different builds done to look for regressions.
So Andy, what you're asking is, are there times where it doesn't clean up its state cleanly?
For example,
Right.
yeah,
And
it's
that's
a
what causes
classic
the bug.
problem.
Right.
You do exactly the same thing 2 times in a row and it doesn't behave the same way.
That's what I mean, and just knowing it crashed will always give you the answer.
I think the answer is no. I think we haven't done that. Raj, every time I see him, not this time, asks me, so Jim, you've been talking about this Terra server. When are we finally going to get it on the internet?
Right.
What's the URL? And May of a year ago, which is to say about a year and a month ago, we told all the world about this great big thing called the Terra server. I'm going to go through the slides very quickly. You have copies of them. We're going to go live on June 24th, Raj. The URL will be www.terraserver.microsoft.com. But don't rush out there yet.
Why is TerraServer.com is already live?
That's these guys. So there are 2 people who are helping us with content, the USGS and Spin2. And Spin2 is the trademark for the Russian Space Agency's satellite image data, which is 1.5 meter resolution. This is Olympic Stadium in Atlanta, and this is 3Com Park up by San Francisco. And you can't really tell the difference, but this is this is about 30% smaller than that, which means that that's twice as good a picture as that because of the square. So the Russians are interested in making money on this. And so we promised them that we'd be live last September. And I believed we'd be live last September. And that's a long story about why we're not live last September, but not here. There's plenty of blame to go around. It's not just us. So they wanted, about January, we'd loaded all this data, and they said, let's go live. And we said, we haven't loaded the USGS stuff, we can't go live. This computer, which is an 8400, the world's largest PC is the way we describe it. It weighs 4 tons, it's 40 feet long, runs NT out of the box, NT Enterprise, runs SQL Server. That's why I say it's actually running the same operating system this guy's running. But it has 324 disks, and 10 gig of DRAM, and 8 processors, each of them about 500 megahertz. So it's a rather more impressive machine than this. And it's now moved to the Internet Data Center. It's actually on the Internet, but we're not telling anybody what the IP address is, and we're putting the final touches on it. But so the Russians have been operating www.terraserver.com to make some money, and I'll show that in a minute. There's the world's largest PC.
What is the processor that it's using?
Alpha.
It's Alpha.
And the next slide is really the slide from hell, and the poor little computer here is trying to make the slide. The next slide shows, well, yeah, that's the slide. So this is the picture, and it just basically shows that there are a bunch of boxes. The blue stuff is the computers, and the other stuff is like the web servers and things like that, and various software pieces that go along with it. This is a test of SQL Server. One of the things that we learned is that nobody cares about backup. People only care about recovery. And we can back up our database very quickly. We could back it up in 12 hours. It was great. We backed it up many times, and we never managed to restore any of the backups. There were bugs in microcode, there were bugs in software, there were bugs in a lot of places. We ended up finding a path through this forest that works, and that's the STC, Timberwolf, Tape Robot, and Elgato Networker, et cetera, et cetera, et cetera. We basically can back up at about 80 megabytes per second, and then you can do the math and figure out how long it takes us. But I think it's about 6 hours to back up the entire system.
And how long to restore?
The same. Restore rate and the backup rate are about the same. So the layout, incidentally, is we have a lot of disks. So the first thing we do is we ask the hardware to make it RAID, and so every 11 disks turns into one RAID 5 set. And then we take the RAID 5 sets and turn them into so-called 4 volumes. And on Friday, we lost the G volume. Now the G volume is 600 gigabytes. And when you lose 600 gigabytes, and that 600 gigabytes happens to have about 80% of your database, you're in a very bad mood. And we moved the 8400 from here to the Internet Data Center, and in the process, some SCSI terminators had fallen loose. And it took the engineers a while to discover that. After the disk came back, NT file check ran, and it runs for 36 hours on a 600 gigabyte drive. After it was done, it discarded 4 of our files, each of them 20 gigabytes. Each tape corresponds to 20 gigabytes, and that's the file equals tape, more or less. So we restored those 4 tapes, and we're back in business. But you get a whole different mindset about things. So I'd like to just give you a very brief demo for the user interface has changed substantially. The picture here is a picture of the world, and where there's green, we have imagery. And right now, it says, okay, we have 697 gigabytes of imagery, and I'm going to zoom in on the United States.
So everybody's then going to say we don't have a terabyte.
It's actually 5 terabytes worth of imagery that we've compressed down to that, and we have about 300 gigabytes more in-house that we're loading, and in fact we're loading data into it right now this minute. Here's coverage. Where would you like to go? Well, that's Minnesota has a senator who
Minnesota has a very good coverage. It's amazing.
So you guys.
Let's go to Redmond.
Okay, so one way of finding it. So that was 109 gigabytes, and now we're down to a mere 3 million rows of data and only 13 gigabytes. So this would probably fit on a richer person's PC. And we're heading into the neighborhood.
This is the Russian database we're looking at now?
This is, so far, this is a coverage map that we got with help from the USGS.
Okay.
And I'm pointing to, I'm going to be lost now. Okay? I have no idea where we are. Does anybody recognize that? Okay, so let's drive to Redmond.
Oh,
Okay?
Jesus, hang on for a second.
Where are you?
Where's your house? This is Maidenball Bay here,
Uh-huh.
right? This is the marina, and this is my house here.
So let's go to Charles' house.
Let's go to California.
Screw that Redmond stuff. So Charles' house probably wasn't built because we're going to have a date up here, and this is July 10, 1990. So this is.
Do you see the ducks? Or the
Oh, is that ducks? Oh, no, I don't think those are ducks. That's.
Oh my God!
So it looks much better on the screen, right? I mean, it is actually.
Oh, right. This is my neighbor. This is this is called Hotel Medina. That's my neighbor.
So where's your house?
This I tore down this house. This was Mrs. Meissner's house.
Okay, so this is the so-called large image that corresponds to that. And so, and each, it doesn't really show, but this is approximately 137 kilobytes and 26 database queries.
So you can see it.
And you can.
Oh, there you go.
You can scroll down, please.
Sure.
Right. This was the first version of my house before I tore this one down. But this is my with the white roof.
Can we go even nearer?
No, that's it. That's 1 meter resolution, and we can. But we
this
can.
is 89.
We can't
And we
peek
can-
into your bedroom yet.
Well, and you can download this. You can download the image from this, and this will create a JPEG on our desktop, and so the USGS makes this data quote freely available, and you can also ask the USGS to mail you the TIFF file. And this works with Netscape. It works with Internet Explorer. We've debugged on everything we can think of, but we learned the true meaning of Woody, which is write once, debug everywhere. This is a Java applet we're staring at here, and it's a nightmare to do Java applets which run everywhere, especially ones that write to your local disk. So these are the tiles. You can see them downloading up there where there they were. But each one of those was a little thing from the database. I guess the one other thing is we've hooked up to Encarta maps, and so this is and you can rightly criticize this for not being the very best DHTML designers. We're actually going off to the Encarta server right now. Hopefully, it will talk to us. Expedia, excuse me. And it's going to send us a GIF, and so that's where Charles's house is. So you can navigate we could navigate to Redmond and then navigate with this and zoom in and out, and then switch over to the image that corresponds to it. So there's several ways of navigating. The other way of navigating is to type in the name. And so we can type in, we have a 1.5 million place name.
CMU.
Well, I was going to try Pittsburgh, but let's try CMU. We can fix that in just a minute by going and updating the database. Doesn't exist, sorry. No such place.
Sorry, Raj. Raj, we hate to tell you.
It'll be fixed in a minute.
It will.
Redmond.
It does. We,
I'll do Pittsburgh.
but let's try Pittsburgh. Because we know that Raj is, I mean, if we're going to disappoint Raj, we might as well do it right now. This is the query everyone asks. They want to see their backyard.
Sure.
So this is good, Raj. The Russians have been watching. So your government was not targeting you,
Right.
but the Russian government, their spy satellites have been watching Pittsburgh, and there it is. And
There's
I-
the stadium.
there's the stadium. Is that
That's Three Rivers. Right down there at the confluence.
Yeah.
okay? But so the good news is we do have Pittsburgh, so we're not going to disappoint Raj too much. I'm sort of at the end. This is we're supposed to be working on scalability. This is definitely has a lot to do with scalability. We've learned a lot from it. It's been great for motivating and crystallizing a lot of work. Why the research guys are doing stuff like this is a research project we're in large. We're trying to get rid of it. We're trying to find somebody else who will own this. Of course, nobody wants to own it. Everybody's very delighted to demo this. They think it's just great, but no one wants to pay for it. So it's being operated by the Internet Data Center.
So what are the lessons, Jim?
What are the lessons? Well, there's the tagline from Godzilla: "Size matters." Size does matter.
More importantly,
But,
what did you not know 2 years ago
well,
that you now know? Because you already knew lots of these things.
right. We can now look customers in the eye and say, you can store a terabyte of data in our database. And this was not true a year and a half ago, and would not have been true if Don Slutz and Tom Barkley and I had not gone down this path, bushwhacked in essence, and then said to the guys in development, hey, you really need to fix this, you really need to fix this, you really need to fix this, you really need to fix this. There are many things, mostly having to do with tertiary storage, some to do with parallelism, that just don't come up until you try something on this scale. In terms of, quote, research, I really call this advanced development. I'm hard-pressed to point to anything that is a research contribution here.
But let's take this problem of 36 hours for backup or something.
Yeah.
What research could be done that would make it possible to do backup?
Parallelism is the only hope we have. And the 80 gig an hour, and it's actually more like, our goal is to be able to do a backup in about 4 to 8 hours. And there are database companies that do a terabyte backup in 1 hour. And they do it by having lots and lots and lots of tapes. And just writing to all the tapes, because each tape will absorb about 8 megabytes a second. And so you then have to, you do the math, figure out backwards how long it will take you to do what you want to do.
So if you wanted to do it in a minute, it's probably going to break everything else, the bus bandwidths and
your pocketbook.
And everything
Yes,
else.
indeed, yes. If you wanted to do it in a minute, it's going to break a lot of other things, indeed. Just parenthetically, Charles has a good friend who works on the Sloan Digital Sky Survey as an astronomer. And Usama Fayyad and I have an NSF proposal with the Sloan Digital Sky Survey folks to take the Sloan Digital Sky Survey, which is going to be about 40 terabytes worth of pictures looking the other way towards, the sky. And that will boil down to about 4 terabytes of imagery and objects that they know about, and then data mining on that. And so there are interesting database and data storage problems there. And then there are very, very interesting clustering and knowledge discovery issues. And the exciting thing about both of these data sets is they're essentially unencumbered. If you have medical data sets or if you have marketing data sets, they're worth a lot of money and no one wants to share them with you. These data sets, people from universities can work with this data and explore and experiment. So, among other things, this is a good corpus for research. So we're about now ready to start to do research on geospatial data.
Great. Thanks, Jim.
Jim.